All right, here is our second set of examples for rotation. All right, we got a bunch of them here, 5 to do. And some of them are going to take a little bit. So good luck to us. All right, so we got a pole. It's attached to the ground. Like say. But it's attached to a hinge, which means that when it falls, right, it falls directly like this. Okay? And I want to know, what is the speed this impacts the floor at, the outer edge. All right, so the force of gravity is changing direction as it falls. So doing this with torque is really hard because you have a constantly changing torque. But we can do it with energy. So the idea of energy conservation, right, is potential, right, U initial plus, and again, you say just say kinetic energy, but I'm going to say kinetic energy linear plus kinetic energy rotational final plus kinetic energy linear final. So these are also both initial plus kinetic energy rotational final. So looking at that, obviously these two are 0. This one's also 0. When you have an object that's only rotating, there is no linear kinetic energy. All right. I know it's not rotating around its center, but we still don't count it. All right. It is being forced to just rotate. All right. So, and I guess U final is also 0, right? Because it hits the ground. It's on the ground. So what is the MGH? We've got a mass 9.8 times, right, the height. What's the height? It turns out in this case it's 0.75. And it's 0.75 because, right, we want the height of the center of mass. This right here, that's the center of mass. The Y center of mass. Right? So, that's the thing. And we have at the end, we have 1/2 I omega squared. It is a thin rod around its end. And hopefully by now you've gotten that that is, you do the parallel axis theorem here. Or you can just know that this is 1/2 times 1/3 times m L squared. And I have omega squared. When I plug all of that in, I goofed. I goofed in my math. I goofed just a little bit. Little teensy bit of goofing. Teensy bit of goofing. Okay, but it's actually okay. When you do this, you get omega squared equals 39.2. And after this, I actually don't know the answer to a bunch of this stuff, so you're gonna have to give me a second to do the calculations here. Can I get a little Jeopardy music here? I don't know what the 39.2 to the 0.5. 6. I should have known that one. That's one that we use all the time. Omega equals 6.26. Okay. I'm not sure that's right. Hang on. We gotta do this part here. Sorry. This is 1/3 times 3 times 1.5 squared. Yes. M is, no, mass is unknown. Sorry, mass is unknown. Oh no, that's 0.75. What am I doing? I didn't goof. My math on my paper is right. Y'all led me to believe that I'd goofed, and I didn't. Forget all this. Sorry. The omega final equals 19.6. And that means squared, which means omega final is 4.43. Okay? And then we have V tangential final is equal to R omega final, and we're looking at 1.5, which means it is moving at 6.64 meters per second. That is the outer edge. Ha! I knew it. I knew I was right all along. All right. Whew. Moving right along. We've got a solid disk right like this, and you got a string wrapped around it, right, and hanging off that is a 4 kilogram mass. And now I want to know, when the mass is released and falls 1 meter, what is the speed of the mass? Okay, so it's going to drop 1 meter. Again, energy conservation, right? I've got height changed, I want to know speed. Energy, energy, energy. Okay, so I've got mgh plus kinetic energy initial, linear initial, plus kinetic energy rotational initial equals energy of gravity final plus kinetic energy linear final plus kinetic energy rotational final. Right, it falls, so we'll make that final 0, and both the kinetic energy initials are 0. So I have the mass changes height, so it's just the mass of the mass, so 4 9.8 times 1 equals kinetic energy final is 1/2 mv final squared plus 1/2 I omega squared. This is 39.2. So what is moving? What is moving linearly? That's this block. This block is moving linearly, so I have 1/2 times 4 v final squared plus 1/2, and this is the disk, right? And so the I of a disk is 1/2 the mass, which is 2, times r, which is 0.25 squared, all quantity times omega final squared. This comes out to be 1/2, or 2v final squared plus, we do all this up, this is 1/8 times 1/2, this is 1/16 omega final squared. Still two things. I don't know v final, I don't know omega final, but here's the thing. This rope is turning the pulley. The rope has the same speed everywhere, and that is the same as the linear, right? So v tangential of the pulley, which is the same as the rope, equals v rope, and v rope equals v center of mass of the block. So omega final, right, this becomes 2v final squared plus 1/16 times omega final is equal to, this is v tangential final over r quantity squared. This comes out to be 2.5 v final, right? We've already squared. We've already established that these two, that this v tangential and this v final are the same thing, right? And so now I can get that v final is 3.96 meters per second. Okay, 3 more. Same pulley, which is nice. Got a pulley, but now I've got a rope hanging off both ends. I've got a mass and a mass. Okay, and this is my, I'm going to make those masses bigger so I can draw a little bit in there. This is 2 kilograms. And up here we've got a 4 kilogram. Okay, this is a connected objects problem. Alright, connected objects. What's the first thing you do with a connected object problem? You draw the positive direction. Second thing you do with a connected object problem is you draw the force diagram. Fg on 4, we've got tension up. Fg2, tension up. Here's where it gets interesting. These two tensions are not the same if the pulley has mass. Something's got to rotate the pulley, and that means the two tensions can't be equal, otherwise the pulley wouldn't rotate. So I'm going to call this T1 and this T2. And that means that on the pulley, I have T2 and T1. Now, what do? I set up the Fnet equations for each of them. So Fnet 4 is equal to FG4 minus T1. Fnet 2, actually, put this further down. Equals T2 minus FG2. And we can summarize this as M, this is 4 A4 equals 39.2 minus T1, and this one is 2 A2 equals T2 minus 19.6. Then we get to the pulley. So the torque net of the pulley equals T2, or R cross T1 plus R cross T2. Okay, so how do we do? Okay, I need to switch something there. You guys didn't tell me that I was doing it wrong. This has got to be T2, and this is T1. Not a huge difference, but it matters. So first off, this is I alpha, right? And that's equal to R cross T1. Well, the radius, right, the force the rope is acting on the edge of the pulley, right? So this is a radius. We know it's 0.25. We also know it's tangential. So if it's tangential, this is sine of the R, well, let me draw it here. So the R, this is the R vector. There's the force, 90 degrees. So that's gonna be T1. That's gonna be sine of 90. Here's what's a little interesting. T1 is going to make the pulley rotate in the positive direction. T2 is trying to oppose that. So it's going to be 0.25 T1 minus 0.25 T2. Okay. I is 1/2 m r squared, right, because it's a disk. And alpha, right, so we have alpha equals, and I'm actually going to put this back into R T1 minus R T2, because I want to cancel one of these R's out. And I get, and the M and the 1/2 cancel each other out, which is nice, right? So I get alpha is equal to T1 minus T2, or R alpha is equal to T1 minus T2. Here's the thing. What do we do next? We add these three equations together, but I have an alpha and two A's. But again, the rope is connected. A tangential equals A rope equals A com of, or A of 4 plus A of 2, or equal to A of 2, right? Those have to be the same, which means that this alpha, we can turn it to A tangential. We've got all the same A's. So how do we do that? Well, alpha, if you divide that by V, right? A equals alpha over R, or alpha times R. Which means that A equals, or alpha equals A over R, which means I can plug it in here, and that gets me rid of my R. So this becomes A equals T1 minus T2. Now I add these three together, and I get 7A equals 39.2 minus 19.6, because if I've done it correctly, my T1s cancel out, and my T2s cancel out. Perfect. And this is going to give me an acceleration of 2.8 meters per second squared. Didn't totally follow, that's okay. I've got another one coming up, but not the next one. Okay, we got a uniform metal bar held horizontally, but it's forced to rotate around a point 0.25. So it's forced to rotate here. Okay. And on this end, we've got 5 kilograms, and on this end, we've got 3 kilograms. Okay, so I want to know what the initial angular acceleration is, right? Which means that I need to know torque net equals I alpha equals torque 1 plus torque 2, right, all of them. So I got to do this thing. So I need to know I, and I need to know all the torque. So let's look at the forces here. We've got FG 3. I know the bar is also 3, but I'm going to call it FG bar, so it's different than that 3. And it's at the center of mass, right, which is halfway along the bar. And here we've got FG5. Right, so let's think about the radial vectors for this. This is the radial vector for that one. This is R5. This is RB. And this is R3. Now, this will tell you whether it's each of these is positive or negative. Right, you do the cross product, you do the right-hand rule. I got R cross B, okay, and at that positive, negative. But here's the thing. Right, these two are both going to be trying to force it clockwise. This is going to go counterclockwise. Clockwise is generally negative, although you can choose in any given problem. So to go back to this, this is going to be I alpha equals R5 cross FG5 plus RB cross FGB plus R3 cross FG3. Right? So, first of all those are 90 degrees, so we can hear the sign. It's just a question whether they're positive or negative. R5, that's 0.25 times 5 times 9.8. And that is clockwise, or counterclockwise, which technically makes it positive. Right? And then we have minus 0.25 times 3 times 9.8. And finally, it's also minus 0.75 times 3 times 9.8. Okay. All of that adds up to being 2.44. Okay. So now I need to find I. So I of the 5 kilogram thing. Well, it's basically just a point charge. I know it's got some area, but we considered it's like, you know, we're considering it kind of a small thing. So this is just going to be m times 0.25 squared. Right, and since the mass is 5, you get 5/16. And then we have, I have the 3 kilogram ball is going to be 3 times 0.75 squared, and that's going to be 9/16. 27/16. I can do math, I swear. And finally we have I bar, and that's going to be I center of mass plus I offset. The center of mass of a bar, right, is 1/12 ml squared, plus the offset is m r offset squared, and that is going to be 1/12 times 3 times 1 squared plus 3 times 0.25 squared. And that comes out to be, I don't know, some number. But all three of these together, can I do this? This is 1/4 plus 3/16. So this is 7/16. Okay, so 7 plus 5, 12, that's 39/16. So I is 39/16, which it turns out is just about 2.44. So go back to here, I've got 2.44 alpha equals this was never 2.44. I wrote down, this is 1.75. So sorry if you're questioning why my arithmetic's really bad, but that was, I wrote down, I looked at my paper in the wrong place. 0.75 Alpha is 0.717 radians per second squared. Make a point about this, right? Is that if I wanted to find the linear acceleration of either of these of the masses, I'd find this angular acceleration first. Okay, if it's rotating, you got to do the angular stuff first, and then you can convert it at the end to the tangential acceleration. Whew, last one, y'all. This time it's another connected object problem. This time we've got a mass on a horizontal surface, then goes over the radius and then down to another mass hanging there. So again, I'm going to go that way as the positive direction. I've got two forces on the hanging block. I've got Fg and tension 1. On the pulley I've got T1 and T2. And on this one I've got T2 and force of friction. And this is the 4 kilogram mass, and this is the 6 kilogram mass. So again, F net 6 kilogram one, right? We've got Fg minus T1, which is 6A equals 58.8 minus T1. F net of the 4 kilogram one is T2 minus force of friction, which is 4A is T2 minus, and the force of friction is going to be M, which is 4. (9.8) mg. It's flat, so force of gravity times 0.2, which is T2 minus 7.84. And finally, we have the pulley. Torque net on the pulley, right? It is R cross T1 plus R cross T2, which is I alpha. I suppose we should just say that the pulley should be a disk. So this is 1/2 mr squared alpha equals RT1 minus RT2. Right, that's directional. T1 is going to try and rotate it in the positive direction, right? We've got the pulley, we've got T1 this way, and T2 pulling that way. T1 is going to make it rotate clockwise, which is the direction we've got is positive, and T2 is going to make it negative. And they're both 90 degrees because the rope is pulling tangentially to the pulley. Okay. Again, we want to get alpha in terms of A, and we know that R alpha equals A, which means that A equals, which means that alpha A over R. I've got 1/2 mr squared A over R equals RT1 minus RT2. And look at that, the R's all cancel out. Okay, that should happen if you do this correctly. This is 1/2. Our pulley is 2, which is nice of me. A equals T1 minus T2. And now we add them all up. So I've got 11A equals 58.8 minus 7.84. And that's going to lead me to 11A equals, actually I didn't even answer, I didn't even get that next part there. So that gets us to A equals 4.63 meters per second squared. All right.